So we can have a dip that just happens to sort of peak about 10 days ago. And 20 days ago, there's a timed reverse version of us having exactly this same conversation. But their past is our future and our future is their past.
So, Owen, the Boltzmann brain.
Yeah.
So you spend your days focused on, the fundamental laws of physics, but then we have this thing, the Boltzmann brain. Who was Boltzmann, first off? The thermodynamics and statistics and all that,
Yeah. So Ludwig Boltzmann was one of the founders of statistical mechanics, which is our approach to trying to understand heat and temperature and so on, understanding it in terms of the idea that matter is all made up of individual atoms colliding with each other and interacting with each other. So prior to that, in the sort of the 19th century, there'd been a lot of development, particularly with the steam engines in the 19th century. And suddenly, everyone knew about heating things up and cooling things down and so forth. But with a steam engine, it suddenly turned out you could get work out of this. You could turn heat into work. You could actually do useful things. You could run factories with them. And so it was in the 19th century that really thermodynamics as a science and an engineering field was sort of developed. But it was very much developed not from the point of view of, as you say, fundamental physics. It was developed in terms of, so we looked at the bulk property of matter. We looked at objects that we were familiar with. Water, you could heat it up, ice, you could melt it, steam could drive a piston. And then just sort of, they worked out general laws to do with this. And these are called the laws of thermodynamics. So, the most obvious one is if you put a hot thing together with a cold thing and bring them together, they reach the same temperature as each other, and the hot things got colder and the cold thing gets hotter until they reach the same temperature. And these were things we'd all seen, but they sort of raised them up to being fundamental laws in the sense that they were believed to be universally valid. But we didn't have any really explanation of why they worked. So at the same time as this was happening, a different area of science, it was actually chemistry, had worked out the atomic theory, the first round of atomic theory and the periodic table famously, so that they worked out things like water was composed of hydrogen and oxygen molecules in the right kind of combination. They had no idea what hydrogen and oxygen atoms were and how they combined together to make water molecules. They just had certain ideas of, that they must get together in these combinations to see the kind of chemical reactions we had. The people who developed statistical mechanics next were people like Boltzmann and the names got Boltzmann and Gibbs and Maxwell, who felt that we really need to be able to explain these laws of thermodynamics in terms of matter being constructed out of these atoms. And they turned out to be really successful. For about 50 years, Maxwell and then Gibbs and Boltzmann and Gibbs really managed to reconstruct almost all of thermodynamics in terms of, of atoms. So the idea is, if you heated a gas, it expands and it'll push against a piston. And they reasoned that this was essentially that if the gas was made out of atoms, and the atoms, when you heated a gas, what you would do is you were speeding the atoms up. And they were colliding with each other faster. And because they were colliding with the sides of a container faster, they'd be exerting more pressure upon it. Now, these ideas, people had this idea for a few hundred years before that. But Maxwell and Boltzmann and Gibbs really actually turned these into working equations and calculated values that made predictions about just exactly how much work you could get out, why different gases, why oxygen behaved one way and argon behaved a different way. So it was tremendously successful. There was still a lot of skepticism, I have to say, because the atoms were still incredibly small and no one could see them. So it still seemed like it was this theoretical fiction.
But it did have prediction in it. So you could predict what something would do, which would give it the fundamental laws of the universe, So is this conceptual thing of the brain, his theory of the brain, doesn't necessarily have, where does it even come from? Because it seems like it's a cosmological sort of idea about the universe. And for prediction, we know there was a Big Bang and we could predict things that come forward from that, but this is something totally different.
Yeah. So there was something, it turned out the people who were a bit skeptical of it pointed out there was something very puzzling, though, about all of these approaches, these attempts. And that's that the fundamental laws of physics, the physics that were supposed to be describing the atoms from which we build up, they have a property of being time reversible. So they work the same in both directions of time. So if you think about this, the easiest way of thinking about this is if you take some kind of processes and you video it and you make a film of it and you run the film backwards, you can usually tell that something's gone wrong. If you crack an egg, you film that, and of course you play that backwards, you get this egg jumping up out of the frying pan and the egg going back together. And we go, well, that doesn't happen. We never see that. But then there are some kind of processes that don't look, that you can't tell so much. So if you have sort of pool balls on a pool table and you just have them rolling across the table and colliding with each other, and you don't see how they started or where they end up, it's very hard to actually tell which direction it's going. If you filmed that and you ran it backwards, it would still just look like pool balls rolling across the table, colliding with each other and bouncing off again. Or if you imagined, one example is if you've got two people throwing a ball backwards and forwards on a flat ground, and they're just throwing and catching really carefully. You could imagine actually if you played that backwards, you couldn't really tell whether someone was throwing or catching if they were both really, really good at it. And similarly, when you get to things like the law of gravity that governs the planets orbiting at that all, it's just things going around other things in circles. If you play it backwards, it's just things going around things in circles. So it looked like all the fundamental laws would look the same if they played backwards or forwards. But then what about all these processes that don't look the same, that the reverse process doesn't happen? Well, all of these processes seem to have something in common. They're typically the processes where if you bring like a hot object and a cold object together, we see they end up at the same temperature. But we don't see a glass of water. If you drop an ice cube into a glass of water, what we end up with is slightly more water at a slightly colder temperature. We never see a glass of water spontaneously forming into an ice cube in a slightly hotter amount of water.
So now we're talking about entropy because we're talking about time, the arrow of time.
So all of these were captured in thermodynamics by the notion of entropy, and that entropy is always increasing in time. But now we have a problem because Boltzmann and Gibbs and so forth were trying to explain all of the properties of thermodynamics in terms of fundamental laws that were time symmetric. And yet one of the laws they wanted to get out was clearly not time symmetric. It governed processes that only happen in one direction and never seem to happen in the other. Now, it took them quite a lot of confusion and false starts and a few decades to sort of come up with an answer to this. And essentially the answer that they came up with was something along the lines of, well, actually, what happens is that the other processes, the ones we don't see, they are physically possible. They're just very unlikely. And they're very unlikely because you'd have to set things up in a very special way to make them happen. So the explanation for entropy is that high entropy states are ones which can happen in lots of ways, and low entropy states are ones which can only happen in a few ways. So if you start off with something just randomly moving through the possible states of the world, it's going to end up in the kind of states that can happen in lots of ways because there's lots more of those kind of states. And it's unlikely to ever find itself coming into a low entropy state because there's not very many of them, and it requires ridiculously special circumstances to produce those low entropy states. And so far that sounds very good, except for the fact we've introduced this word likely. We've introduced probability. Now, in many ways, this was the thing that statistical mechanics did. It actually took these fundamental laws of atoms and then added probability theory to it. But there's still something puzzling about that because probability theory doesn't have any time symmetry in it either. We can make probabilistic predictions about the future, but we can also make probabilistic predictions about the past. We say things like, is it likely that the dinosaurs were killed by an asteroid? We're not certain about it. So we think there's some probability it's true. And then we look for evidence, and that evidence actually raises our certainty or reduces our certainty. So we can do investigations about our lack of knowledge about the past. And that's still probability theory. And that uses probability theories in exactly the same way as we say, well, we don't know what the weather's going to be next week. So we'll take what we know now and we'll make predictions about what the weather's going to be next week. So probability theory in itself can't be the answer to the problem. It can't tell us why one direction or the other is actually the one we see happening. It can't tell us why some processes happen and the other processes don't happen. We need to bring in some additional thing as well. And that additional thing seems to be, and this is a case where we sort of know what the answer is, but we have trouble working out why we should be allowed to call upon this answer. The answer is that the process has to start off in initially low probability states, which means things have to start off in initially low entropy states. But we don't have a reason why that's the case at the moment so far. Now, Boltzmann came up with this wonderful suggestion. And he said, look, suppose the universe is infinite in time. Suppose we've just been around for a very long period of time. Then, well, what happens is the universe is going to just go through randomly through all the different possible states. If we imagine if we have our glass of water, perhaps, and we completely isolate that, we put it in a box and we thermally shield it, so we can't have anything coming in from the outside, and we just let it sit there for a period of time. Well, one of the states that can randomly form into is an ice cube. And a lot of the states that it can randomly form into is a glass of water. As we sit there at any given time, there's so many more states associated with being a glass of water than it being ice. It would be ridiculously unlikely at any given time for it to be an ice cube. But every now and then, it will become an ice cube. We would have to wait a very, very long time before the probability of it becoming an ice cube turns up. It's like if you keep rolling dice, a lot of times, if you roll them and roll them and roll them and roll them, eventually you're going to roll a 6 10 times in a row.
Wait, I have a question
sure.
about the ice, because first of all, I have a lot of questions because I'm really, I don't understand most of what you're talking about. And that's okay. It's good. I want to understand though. You said you're going to put that in a box, the glass of water in a box,
right?
And you're not going to introduce any other element. It's right. It's sort of in a, I don't know. It's like in a tomb or something. How could then, without introducing any other element, could it go back and forth between being water and ice? You would have to introduce cold.
Right.
Wouldn't you have to introduce another element to transform it, or no?
Well, you wouldn't have to. What the energy would have to go somewhere, but it might be that the glass holding the water becomes a bit warmer, and then the water itself ends up a bit colder. And the glass gets hotter and hotter, and the water gets colder and colder until the water becomes ice.
Does the water ever evaporate? Could the water ever evaporate, or no?
Oh, well, that's also one of the processes that can happen. The water could evaporate. We've got this sealed up box. The water can evaporate into the air as well. And at some point, we might find all of the water is evaporated into the air. But that means it's actually had to take energy out of its surroundings. And that means the glass must have got colder for the water to all evaporate.
But really what we're talking about is time, right? With over a long enough period of time, all the possibilities will occur. And we just maybe haven't been around long enough to see the possibilities that we think are unlikely.
Yeah. So that's the thing. We just cycle through all the different possibilities. I mean, we go randomly through it. It's not so much a cycle. It's not really something that is guaranteed to happen. We just randomly go through all the possibilities. And eventually, even the really rare things will happen. Mm-hmm. Now, Boltzmann said, okay, but look, we look around us and what do we see? We see that entropy was low in the past and it's getting higher in the future. Maybe what's just happened is, apply this to the whole universe. The universe as a whole is just randomly going through all the possible states. Sooner or later, it's going to go into a low entropy state. And then once it's gone into a low entropy state, it's going to gradually move back to being a high entropy state. So it'll go through this process of, it'll sit around being in this kind of not particularly interesting high entropy state where nothing's going on. And then if we wait long enough, it'll move into a low entropy state, reach a lowest point, and then move back into the high entropy state. Now, the first thing is if we happen to be on the part of that curve where it's moving from low to high entropy, it's going to look like the world looks to us. And he goes, okay, then maybe that's the reason why. If you just wait around long enough, my theory predicts that what we see will happen. But he also made another remarkable suggestion, was that if we were on the other side of the curve, someone on the other side where it's moving from high entropy to low entropy, all of the processing there would be happening in the opposite direction. So anyone on the other side of that curve would actually be thinking time was moving in the other direction. So they would perceive time in the opposite direction to us. And he said it's like in space, there isn't up or down. There's just the direction you're facing. Well, similarly, in time, there isn't past or future. It's just where are you sitting on the entropy curve? Because wherever you are going to perceive the future as being high entropy and the past as being low entropy. So all it has to be is these bumps, these fluctuations to lower entropy, and that'll explain why there are these low entropy states in the past that it accounts for everything we can see. And that seems like that's great. That's completely time symmetric, because you take that curve where it's going along and it goes down and then goes up again and then it's going along, and you turn that around and it looks exactly the same. But on both sides of that trough, on that valley, you've got people who are seeing, in their sense, a low entropy past and a high entropy future, but they're seeing past and future turned around relative to each other. And this was a, quite an enormous insight. Nobody had really thought of things that way before.
So what does that, mean? It sort of sounds like when we look in a mirror, like the mirror, no matter where you look, the light reflecting back is always at the same exact distance to what you're seeing, right? So is it, I guess the question is, right, we know about the Big Bang, we know how to test for that, we know how to test for a lot of these things. How do we test a theory like this?
Well, so the Big Bang's a bit tricky because they hadn't actually come up with a Big Bang theory at that point. I mean, Einstein hadn't even come up with the special theory of relativity at that point. People thought that the universe either had been created by God at some point in the past, or else probably had been eternal and had been around forever and didn't have a start. So from the point of view of time had always been, the universe had always been around, Boltzmann's theory seems to be looking quite good. The problem with Boltzmann's theory is once people started to actually look into this more, and this is where we get to the Boltzmann's brain problem, is that eventually if you wait around long enough, you'll get this big dip, so the valley, where perhaps the bottom of this valley looks something like, say, the early stages of the universe to us. Okay. If you wait around over a large amount of time, you'll get small dips and you'll get large dips. And the small dips will happen a lot more frequently than the large dips. So if you're thinking about probability in those terms, then what's actually you can say is that, well, small dips are more likely than large dips. So if we look around at the evidence we have available to us and we ask, what's the most likely thing? Well, the most likely thing is we're in a valley which is just small enough to account for everything we can see, but no smaller than that. We now actually start to get into a lot of trouble because I suppose if the solar system is currently exactly as we think it is, well, that valley actually just goes back only about a long enough time for some light to cross the side of the one side of the solar system to the other. All we appear to be in is this little island of order that's sort of been created just a short while ago that looks exactly like everything we actually see, is in fact like everything we actually see, but we're actually completely mistaken about what was in the past, because all of the sort of records that we have in the past aren't really true. We have this sort of entropy gradient, but it only goes back far enough to actually account for us being in the state we currently are. It doesn't need to go back any further than that. So we can have a dip that just happens to sort of peak about 10 days ago. And 20 days ago, there's a timed reverse version of us having exactly this same conversation. But their past is our future and our future is their past. And they're talking about how maybe there was a dip. What's for us 10 days ago, and for them is 10 days ago also, but it's in intervening time between us.
Is it kind of a quantum mechanics kind of idea? Because part of it, because in quantum mechanics, time can go either way. And, when we think of this, we're thinking about time going in different directions, although where we sit on the curve is a different, place.
Well, we don't really need quantum mechanics for this at the moment. I mean, quantum mechanics will have this problem. It will come up in a different way. All that matters is that the fundamental laws of physics are time symmetric. That's the thing. And that's going to be that was true of classical mechanics. And as far as quantum mechanics is concerned, it seems to be true of quantum mechanics for this particular kind of problem.
Okay, these are theoretical ideas, but to translate them into the real world, I mean, what is that? What are we saying? If you were to
Well, it could be 10 days, it could be 10 minutes. It's like,
well, no, but then
we don't know where we are.
I know, but I just want to hear you, Owen, say what do you infer by that, which is pretty dangerous to say that, the history is only 10 minutes ago. I mean, that's just like very self-involved, self-referential.
Well, I mean, right? The universe is the universe. I don't think it's,
right, but that's the part I'm getting. I don't understand because I watched your video and trying to understand, been reading about it all night, been dreaming about it all night. Okay, because I'm trying to understand what's the value. I guess why is this important? Why is this insight important? For me or for anyone watching this.
Right.
Well, that's why is physics important for anybody watching it.
I mean, why though?
Physics is just to know, the origins of the universe.
Yeah. I mean, I think partly because the problem gets worse, it does get even more self-absorbed. It gets ridiculously self-absorbed. But not only does it get self-absorbed, this line of reasoning ends up going horribly wrong. There is actually something has to be wrong with this line of reasoning. And the interest in trying to figure out is what went wrong in the line of reasoning, because maybe that will point us in the direction of new lines of research. Right. So the way it gets like ridiculously self-absorbed is like, okay, I just said, suppose the solar system is around here. But what's my evidence for the solar system being around? Well, it's actually because, I turn on the TV and I get all these signals. Once I've got to the point of accepting this, I just have to say, well, the most likely I'm sitting here with the evidence available to me. And the most likely explanation of the evidence available to me is an even smaller bump. It's an even smaller bump of low entropy that just contains my room that I'm sitting in right here. And you guys, sadly, are a pure fiction. You're just a bunch of light signals that happen to have randomly arrived on this laptop, and you don't have any real existence at all.
That's probably true.
But it's even worse than this, because actually I don't really have any evidence for the existence of the room I'm sitting in. A more likely scenario than that by far is there's just my brain. And my brain is sitting in this cosmic soup, and it came into existence randomly, let's say 25 minutes ago when this started. And since then it's being bombarded with random fluctuations from a cosmic soup that's making me think that everything that's going on.
All right, now you're in a Charlie Kaufman film. Now we're getting somewhere that I can.
Now there's a problem with that. Now that might seem, if I follow this line of argument, that's the most likely scenario consistent with my knowledge. So I should believe that, really, if we use probability theory. But there's a couple of other things there. It's like, well, why have I come to believe this in the first place? And that's the Boltzmann's brain scenario.
Why should you believe that? Because of the probability. Why would probability be important for that?
So the role of probability is important because small bumps are overwhelmingly more likely than large bumps. So because small bumps are overwhelmingly more likely than large bumps, the most likely explanation for any experience I have is a small bump rather than a large bump. The very large bumps that suggest not just the solar system, but the whole of the universe came into existence as we more or less see it, are overwhelmingly less likely over time. It is quite astounding orders of magnitude. I mean, we talk about things like how long would you have to wait for all of the gas in one room to gather in one corner? And you'd have to wait lifetimes of the universe as far as we understand it. But the actual probability of the universe itself coming into existence is just, the words fail me to describe how unlikely that is on those time scales, on how long you would have to wait. And while you're waiting for those to happen, there are lots and lots and lots of times that just a brain pops into existence, just long enough. So if you know nothing about what kind of entropy fluctuation you're on, what kind of bump you're on, just on the evidence around you, the most likely explanation for your experience is you're in a tiny bump, just small enough to account for your experience. But that means you're a brain in a soup and nothing that you actually believed was true. And therein lies the problem. Because we got to this argument using probability theory and the fundamental laws of physics. But why do we believe the fundamental laws of physics? Well, we believe the fundamental laws of physics because a lot of scientists in the past did a lot of experiments and tests and worked out this is a pretty good description of how the world seems to be working. But if we now come to the conclusion we're actually a brain in the soup, we no longer believe any of that was true. We no longer believe there were any scientists in the past. We've suddenly ceased to believe one of the key things that led us to believe that we are a Boltzmann's brain. So there's a phrase for this: this is incoherent position to be in.
It's very anxiety producing. I just want to say, if we're just a brain and there's no reference to anything, then why are different brains coming up with these theories?
Well, there may not be different brains. There may just be one brain.
Okay, well,
it could be one brain. At any given time, there may be one brain. They're disconnected. There may be different times. There's many. Every now and then, there's a brain that comes into existence that thinks the universe obeys the laws of thermodynamics. Every now and again, there's a brain that comes into existence that thinks the universe is being carried on the back of a flying unicorn. Yeah, just any of these things will just happen briefly.
So, what is the moral question about our behavior in this world that we live in?
Well, if we actually if we believed this conclusion, it's hard to know if there's any kind of moral consequence, because there is simply nothing we can do with that kind of conclusion. All of our assumptions, all of our records of the past, all of our beliefs about the way the world is, all just turns out to be hopelessly mistaken. Now, that seems catastrophically bad, but at the same time, it turns out it actually demonstrates we shouldn't actually believe that. Because the only reason we believed that was because we believed in the laws of physics. And the only reason we believed in the laws of physics is because we believed that our records of the past are true. So if that argument then tells us that we shouldn't believe our records of the past are true, then we no longer have to believe the conclusion of it.
Right, which means there's no global warming. There's
exactly. We abdicate. There's no responsibility for anything.
I mean, luckily, this is just a theory,
Yeah. But the thing is, if we don't believe the laws of physics are true, then we don't believe that we are Boltzmann's brains. Because the only reason we believe we're Boltzmann brains is because we did believe the laws of physics were true.
So it's a contradiction within a contradiction.
Yeah, it doesn't mean we should disbelieve the laws of physics. It means something's gone wrong in our reasoning. We can't put together the different elements that went together to get us to the Boltzmann's brain argument, because the conclusion is inconsistent with our assumptions. So something in the argument has to have been gone wrong. And identifying what's gone wrong is the thing. And it doesn't mean we have to say the laws of physics are wrong. Right. We would only think the laws of physics are wrong if we were convinced of the conclusion. But if we don't believe the laws of physics are right, we have no grounds to believe the conclusion. It undermines itself.
So when we look at the, these recent discoveries about quantum information, in some ways you could say entropy is just about information, right? You get more information as you go forward. Does that affect this theory in some way?
There are some attempts to do it. What we have is really three things that go into getting to the Boltzmann's brain conclusion. So at least one of these three things has to be wrong. So one is there is just maybe something not right about the laws of physics. It doesn't mean we have to throw them out altogether. It could be the key thing that came from the laws of physics was that they're time reversal, symmetric. They're time symmetric. Maybe we were wrong about that. Maybe we should look for evidence that the laws of physics aren't time symmetric. So that's one option.
Right.
I think that's quite a good option, actually. So you just think that maybe there's a modification. So maybe we look for quantum theory to see if things like wave function collapse in quantum theory might provide a slightly different evolution. So we have the introduction of irreversibility. It enters in a different way. Now, that would just completely block the whole argument at the start. A second argument is what I would refer to as the sort of transcendental argument. It's the epistemology. It's the why do we believe what we believe kind of argument. And this essentially goes on the idea of like the general pattern of these arguments come across in skeptical scenarios like Descartes imagining a demon that is systematically deceiving us about the world, or David Hume suggesting the problem with induction is just because something's always happened this way doesn't mean it's always going to happen this way, where all of these things are doubting that the world is more or less the way we see it. And the sort of the transcendental response to this is saying, well, look, we don't know how the world actually is in itself, but in a sense, if we doubt everything, we can't do anything. There's nothing we can do with that kind of argument. So in a sense, we're kind of forced to assume something about the world is kind of structured in the way it sort of seems to us, and then work on that basis. And so maybe we've got the details right, but we just have to make an assumption that the structure we see in the world has to be in some way reflective of structure in the world, because otherwise, what else are we going to do? So that's a kind of transcendental argument. And which makes us just shrugging our shoulders to say, oh, well, there we go. We're not Boltzmann's brains, so the world was just at a low entropy in the past. The third argument, I think, is about, well, maybe there's something wrong with the way we're using probability here. And this is where it maybe connects into ideas like information. And it says, well, maybe we were just wrong to say, when we are thinking about our beliefs about the world, it matters that it's our beliefs, and it matters how we interact with the world, and it matters with information. If entropy is something to do with us acquiring information and processing it and then acting upon that information, then there's just a fundamental asymmetry to us there, and that maybe the asymmetry was embodied in us and the way we interact with the world in the first place. There's some problems with that, in that it's not clear how it's actually solved the problem, unless it's going to say there's something different to us, that the laws of physics don't apply to us. If we think that we are just physically embodied agents constructed out of atoms and molecules according to those same laws of physics, then it's not obvious where it is that asymmetry in us can come about.
If we, for a moment, just assume that, we're not Boltzmann's brains, right?
Yeah.
And we
should assume that.
Right. So we assume we're not, and we look back to Newton, say, as the beginning point of the study of physics, right? Going forward, maybe we've been at this a few hundred years, how long do you think in your mind it will take to really get an understanding, is there a chance we'll get an understanding of things like time and entropy and things like that? Because we've certainly made incredible rapid progress in terms of if you just look at how fast things are going, but is it enough? Is it and how long do you think it'll take to really get an understanding of some of these things?
I don't think there's a clear program at the moment. There are hints in quantum field theory. So if we take quantum mechanics, and so that's just generally what we often say when we're talking about atoms and how atoms themselves are made up of electrons and protons and neutrons. But as we now believe that protons and neutrons are themselves made of smaller and more fundamental particles called quarks and gluons and neutrinos. And of course, there's the Large Hadron Collider at CERN and Fermi and other particle accelerators at Fermilab. And they have a deeper picture of what the fundamental laws are. Now, there's an interesting feature of that. At least some of those processes don't seem to be time symmetric. At least some of the fundamental processes that have been studied in these high energy physics things don't work the same way when we run the film backwards. Now, they're not really sure what to do with that. There's a couple of problems with it. The first problem is those particular individual processes just are very rare, and they involve things called K-mesons, which don't seem to have any relationship to coffee cups cooling down and ice cubes melting in glasses of water. And it's not clear. We on the one hand, yay, look, here's some fundamental laws of physics that are not time symmetric. So maybe there's the solution. But on the other hand, that doesn't seem like a good explanation, because it doesn't seem how that can actually explain why these entropy processes are taking place. But there's hints there that maybe physics could be time asymmetric. Actually, most of the programs in high-energy physics, such as superstring theory, think that the deeper explanation in high-energy physics is going to make that time asymmetry go away. And that's going to restore a full time symmetry. So from my point of view, that's terrible. I want there to be a fundamental time asymmetry, because then that'll get us out of this whole problem. But much of the gist of research in quantum field theory and high energy physics is actually looking for solutions that are going to restore a fundamental time symmetry. So I'm kind of hoping they're going to fail, to be honest, and it's going to have fundamental time asymmetry embedded in our laws.
I have a question about your students.
Yeah.
With this sort of, Jesse was, talking about there's more information, there's AI, there's all of these, kind of neutrinos. We did go under the ground. We did go to the Fermilab, actually. And
yeah.
but that was kind of amazing. Another story. But Are the students asking different questions now? And because we have more, in a way, more tools, we've built more tools, is the thinking changing? Are the questions changing? Are students thinking about, ideas here? Are they throwing Bozeman's brain out? Like, what is the thinking right now? What's the trend really?
So there are some trends within quantum theory and the attempts to understand quantum theory. People looking at quantum information theory occasionally do try to recast the formalism in a particular way that seems to have operators in them that aren't symmetric in time. So there are various kind of processes. I don't know if you've ever heard of a process called decoherence that looks like it's time asymmetric. But every time we look closely at those kind of operators, they always seem to be an approximation to another operator that is actually time symmetric when we look a little bit deeper. So if we want to reformulate quantum mechanics, we need to go a little bit deeper than just talking about things like decoherence. There's some also current process interested in the notion of causality and whether we have a notion of quantum causality, because causation is an idea that we're all kind of familiar with. There's a cause and there's an effect. I throw the ball, it causes it to fly through the air, and someone catches it. And that seems to be time asymmetric because causes always come before their effects. Now, that's a little bit controversial, but about 100 years ago, a lot of physicists have sort of abandoned even talking about cause and effect as anything fundamental because it looked like the laws of physics were time symmetric. So how could there be anything? So they didn't find anything called cause and effect in fundamental physics. There have been some attempts to sort of reanalyze that again with quantum theory, to say, well, maybe quantum theory it has a problem with the old notions of causality, and that if we come up with a new notion of cause and effect, for quantum theory, a quantum causality, maybe this is actually going to introduce a time asymmetry. At the moment, I would say it's still very speculative, and I've not seen anything that doesn't have the same problem as the decoherence problem. But when you look closer, it's always just a time symmetric process where you ignored part of what's going on. So there's certainly desires that. Perhaps for me, what would seem the most promising is just to say, look, we've got to change the laws of physics then to introduce a time asymmetry. So there's a number of proposals, perhaps, for changing quantum theory to introduce a process called wave function collapse. Well, at first sight, this looks like it does the job. It's a completely random process. And so you have a quantum state, and then it randomly jumps into one of a number of different possible states. And at first sight, this looks like this is adding the necessary thing. But it turns out if you look closer again, even though it's random, it can still be a bit too time symmetric. So it's not enough just to have wave function collapse. You need to have one that is, again, it's got to put time asymmetry in there. So there's a number of physicists. So Roger Penrose is probably the most famous figure on this front that thinks that attempting to link quantum theory to general relativity is only going to work if we have this notion of wave function collapse.
Oh, thank you so much. I'm trying to understand a little tiny piece of it, but I did find some trivia though in my search, which is apparently when he was they put him in like in a graveyard with a bunch of regular folks, and then later when some of the physicists discovered him and really revered him, he was reburied with Beethoven and Brahms, I think. That's what I learned. Right. I don't know if it's true or not.
Yeah. I don't know. That's interesting. Yeah.
Thank you for these insights. It's been great. Fascinating.
Thank you so much.
Yeah.
Thank you. Thank you very much for your patience for listening to me.
Yeah, it was great.
Thank you.
Bye, you guys.